Okay, so we've seen that the physics of the situation give us our general equation when you have an impulsive force. We've seen the solutions when your applied force is 0 for two different situations, and we've alluded to a third. When we start at the initial position with a unit velocity, so that the graph is initially moving, initially has a slope of 1, and y of 0 equals 0, so we start at position 0. So, gives us this sine curve. If we change the conditions to where we start the timer when the thing is out here and apply the initial impulse at that point, and actually we're not applying initial impulse, we just start the timer when the oscillator's out here, no applied force. That changes the 1 in this equation to an s, and we get a cosine of t. So we want to understand that. Okay, now let's take a situation where we do have a non-zero applied force. Okay, a unit impulse at time 2 pi. In this case, up to 2 pi, the unit impulse hasn't been applied, so we know that this thing is going to follow a sine curve. And then we apply a unit impulse at this instant. Well, that's like the thing does one oscillation, then we slam it. It's going to go into a bigger oscillation. So we know that the thing at this point is going to discontinuously change its velocity, and it's going to go to a higher velocity, and it's going to go to a greater amplitude. And just from energy consideration, the pressure at amplitude is going to be square root of 2. I'm not going to work that out. That's just a little bit of trigonometry after we get our solution. Okay, so our differential equation is going to be y double prime plus y equals delta of t minus 2 pi. Doing the Laplace transform, we get s squared L of y. And then our y of 0 is 0, our y prime of 0 is 1. So that's going to be minus 1. And I'm skipping a step here, but we did the step previously, so make sure we understand where that 1 comes from. It's just part of the Laplace transform of the second derivative. Okay, then it's going to be plus Laplace transform of y equals the Laplace transform of delta of t minus 2 pi. Now I'll just write off to the side here that the Laplace transform of t minus t naught is e to the negative s t naught. Okay, so that in this case t minus 2 pi is t minus t naught with t naught equal to 2 pi. We get e to the negative 2 pi s. Fair enough? Well, now we can say that, and I'll do one step of the algebra here, s squared plus 1, see how I almost wrote down a minus there? I'm famous for doing that. You always got to check me, because I do these things and don't always recognize them. And my goal is to give you the idea. I don't mind making a few errors. Sometimes I make too many and I do mind that. Okay, anyhow, we have this, and this is going to equal 1 plus e to the negative 2 pi s. Then Laplace transform of y is 1 over s squared plus 1, which we recognize. It's just going to give us our sine curve. Okay? And then that's going to be plus 1 over, well, it's going to be, it's not 1. See how I write things down out of habit? I keep my head in the game, I don't do that. Okay, thinking ahead of what else I'm going to do. Okay, e to the negative 2 pi s over s squared plus 1. So that y equals the inverse transform of 1 over s squared plus 1 plus the inverse transform of e to the negative 2 pi s over s squared plus 1. We know that the Laplace transform of e to the alpha s, or the e to the alpha s, multiplied by Laplace transform e to the negative 2 pi s times whatever shifts the graph of the whatever 2 pi s units to the right. Meaning that and again, that's something I assume we understand. The result here is that we get the sine of t plus this graph shifted to the right. This would be a sine of t minus 2 pi, because we're shifting to the right, and also times the Heaviside function of t minus 2 pi. Again, we're assuming we understand the shifting behavior and so forth, and the fact that this function is going to be 0 up to when t equals 2 pi, which of course corresponds to the fact that we're applying the impulse at t equals 2 pi. Okay, this is a unit impulse applied at t equals 2 pi. That means that for, I said the amplitude would be the square root of 2 pi. I mean square root of 2. This isn't fitting with my concept of energy conservation, but I'm not going to worry about it right now. I got to resolve something in my own head. Yeah, that happens. I mean, resolution doesn't always happen, but plenty of situations where I got a discrepant idea that I need to resolve. You want to get in the habit of doing those things. Okay, don't use me as a good example. You know, I'm not as sharp as I used to be, so I don't resolve those things very quick, instantly in a video. Okay, so anyhow, here's what we have. Okay, and I'm not claiming that I could always resolve them quickly either, but I used to be able to resolve them. That one I should be able to resolve real quickly. Okay, digression aside, we have this. This means that up to here, up to the 2 pi instant, this function is 0 because of the Heaviside function being 0 up to 2 pi. Okay. After that, we have the Heaviside function, and let's indicate that by right here is our sine of t minus 2 pi times u of t minus 2 pi. Dotted line that goes along 0 up to here, and then it follows the sine curve from there. And of course, we have our original graph. The original oscillation persists. So I'll just kind of draw that. And maybe you can see them both, but what we have then is both a white curve and a green curve. And they look exactly, they're, one is right on top of the other. So that when we add the two, we get double the amplitude. Okay, so at this point, things change. Now you want the whole function Well, the whole function is this and then this. I could draw all of that in one color, and I'm tempted to do it, but I'm not going to do it. Just your total solution is this and then this. And again, pretty much what you expect. You got this thing oscillating. Okay, unit impulse here, boom, goes into a greater oscillation, into an oscillation of greater amplitude, and looks to me like 4 times the energy. I'll figure it out later. I mean, I know that's got to have 4 times the energy. Okay. Well, that's first application of your Heaviside, of your Dirac delta function and the resulting Heaviside function.